Hi everyone. This video is the solution for example 2 of beam deflection. In this case, we have a cantilever that has 6 meters, but now has two loads, one of 60 at the beginning and then a load of 90, 2 meters from the tip. So same as before, let's assume our axis to go from left to right, and therefore the first thing we need to do is to write our moment equation. This is an interesting problem because if we think that z is in the first 2 meters, let's say it's at that green spot over there, the moment will be just minus 60 times z. And minus again because it's doing tension on the top, this type of moment, and times z because that's the distance between the load and the application. But now, if we think that our point is, let's say, here, then our moment equation should be something different. Should be something like 60 times z, and again with a minus because it's causing tension on the top. But then we need to add minus 90 times z minus 2. The z minus 2 being the distance from the tip all the way to this point is z, and then we remove 2 to get this distance here between the load and the green point. But now, how can we have two equations that describe the moment depending on different points? And here's where it comes the Macaulay's method. And the Macaulay's method is a trick to make sure we can write this in just one single equation. So I'm going to show you how this is done. And this is done taking into consideration some special function, some trick function that is called the Macaulay's function. So if I write this as 60z and then minus 90, and then I'm going to put here some square brackets to indicate that something different is happening here. So the idea of these square brackets is a Macaulay's function. And what a Macaulay's function is, if we take some value of x and we put these two square brackets around, and again, just to indicate we're using a Macaulay's function, we get two different outcomes. If x is negative, we're going to assume the value of the function to be equal to 0. But if x is positive or equal to 0, we take the value of the function to be equal of x. So what's the trick here? What we're trying to say here is if z is bigger than 2, so if z is bigger than 2, we're talking about this second green point here, then this is going to be positive. Z minus 2 is going to be a positive number, so we take into consideration this part of the equation. While if we're thinking about this first green dot, when z is less than 2, this is going to be negative. This part here is negative. And the Macaulay's function, the only thing it says is if what's inside is negative, we take it to be 0. So this is just a little trick for us to consider that the load of 90 only acts when z is greater than 2. So that's basically it for this problem. And once we accept the Macaulay's function and how it works, then everything is exactly like it was before. So this would be our moment equation. For example, we could test the moment when z equals to 6. And what do we get? We get minus 60 times 6 that we get already from first year structures. It's just force times distance, minus 90 times 4, which again we get from first year structures. And this will still be minus 720. So what I'm trying to say is the Macaulay's method is just a little trick. This brackets here, it's just a little trick to help us take into consideration loads that are not in the beginning or the end of the beam. So now that we have this, we can continue to say that our curvatures are nothing more than minus m divided by EI. So we can write this as 1 over EI times, and I'm going to take the moment equation and flip the sign and get 60z plus 90z minus 2. And now the next step is to get the rotations. So again, rotations being the integral of the curvatures, dz. So that we get 1 over EI times, and this will be 30z squared plus 45z minus 2 squared plus c. And finally, the deflection is y of z is nothing more than the integral of the rotation, dz, and that's equal to 1 over EI This will be 10z cubed. That there should have been 45. So 45 divided by 3 should be 15. Z minus 2 cubed plus cz plus d. So now we can use now the boundary conditions to find c and d. Let's look back into the structure and realize that our boundary conditions are both at z equals 6, so here at the fixed support, and the rotation and the deflection are both equal to 0. So let's write that down here. We know that our boundary conditions, let's just write here B, C for boundary conditions. So y of z equals 6 must be 0, and the rotation y dash when z equals 6 must also be 0. So now we can use these two to find our c and d. So let's replace the rotation one first, so then we can find c straight away. And here we have 1 over EI times, and then 30 times 6 squared plus 45 times 6 minus 2 squared. And here you can stop and think that because 6 minus 2 is going to be positive, this keeps the value of 4. Okay, it's the same as 45 times 4 squared. Well, if that part was negative, then it would go to 0. And then we get plus c, and we know that all of this has to be equal to 0. So now we can recalculate this and get 1 over EI times, and use the calculator to get 1800 plus c equals to 0. And here we can get, therefore, that our c is minus 1800. So now we're in a position to use our other equation of boundary conditions to get d. So let's replace this. 1 over EI times, and now 10 times 6 cubed plus 15 times 4 cubed plus minus 1800. So it's not plus here, it's minus 1800 times 6 plus d equals to 0. So if we now use the calculator here, we're going to get that 1 over EI times, and now this part is minus 7680 plus d equals to 0. So therefore we can get that d is going to be equal to 7680. So now that we have our c and d, we can rewrite our final equation for deflection, which is 1 over EI times 10z cubed plus 15 z minus 2 cubed minus 1800 z plus 7680. Finally, if we want to find the maximum deflection, here we could say straight away that the maximum deflection, since this is a cantilever, will be here at the tip, so will be when z equals to 0. This simplifies a little bit the equations. So when we replace everything with z equals 0, again, very important, when we do it here, 0 minus 2 is minus 2, but because it's the Macaulay's function, we take this as 0. So what we're going to get is 0 here, 0 here, 0 here, so we just get 7680 divided by EI. And again, the fact that it's positive means it's going to go down. So I'm just going to delete this green part, but please pay attention when you get to this Macaulay's function. Remember that if your values inside the brackets are negative, you take it to be 0. So this concludes this problem. Thank you for watching this video and have a nice day.